afternoon, everybody, and welcome to our last session of FlowcytometryUK. I hope you've all enjoyed the meeting. It's been really fantastic. So our last speaker is very well known to all of us. He's the author of Practical Flow Cytometry, but we all know that as the Bible of cytometry. So Howard's books and regular postings on the Purdue site have been informative and have entertained generations of cytometrists. You might know about his laws of cytometry, which include things like the zeroth law. There's no magic in flow. I used to use that all the time to my users in my lab. There's no magic in flow. There's always a logical reason why things do or don't work. A lot of these laws are common sense, such as the third law. What's in the bottle isn't necessarily what's on the label. But then some of those laws need a little bit more explanation. And I think some of these we actually need to ask Howard more about them. For example, the fourth law is most babies aren't born in supermarkets. I would highly recommend reading up his laws of cytometry in the Bible of cytometry. So Howard today is going to give us a historical overview of his time in cytometry. And as you'll see from the programme book, he's written it in rhyme. So I think we have promised a very entertaining and insightful talk. So now it's time to introduce our great flow hero. Ladies and gentlemen, put your hands together for Dr. Howard Shapiro.
Thank you very much. I love this. Okay, well, I didn't write the whole business in verse. I've done that, I've signed papers, but then that gets a little hard to follow. And the 6-decade log, there's a pun in there, or a pun or two in there. What do I do, just hit the down arrow? Yeah, okay. So anyway, starting from the beginning, you heard some of this during the discussion between me and Lee Herzenberg the other day. And yeah, the son of a physician and a biologist, I was kind of, which medical school do you want to go to? And so I had the stethoscope at 3 and the microscope at 6. And then the dissecting kit, which, as I point out, would get my parents arrested for child abuse. But the thing something that I explored is that there's a Dutch influence here. After all, Van Leeuwenhoek was Dutch, the father of microscopy, really, and there were so many other people in the Netherlands who were involved in this. And where I grew up in Brooklyn, New York, that's Brooklyn is Brooklyn. There's a town in Holland named Brooklyn, and Brooklyn is named after that town. And we had, our public high school was Erasmus Hall High School, so it was kind of. And when I was growing up, my mother had interrupted her PhD studies to raise 2 kids, and so I was staining slides for her and I was doing gram stains and acid stains and Fourier stains, and I was reading the books on her shelves. So my first cytometry experiment was actually done when I was 15, almost 60 years ago. And so that is 10 decades, and this, if you will, is my log of what I was doing for 10 decades. But that will change. And the question which came up, which I tried to answer in a science fair project, was, my father said, well, we take tissue samples post-mortem from these cancer patients we treat, and we look at mitotic indices, but does that really work? Why don't you look that up? So I went to the library, because we didn't have PubMed in those days, and then never mentioned, we didn't start putting the medical literature onto computers, big computers, until 1966. So in essence, 1966 is what physicists would call an event horizon. If you want to look up anything on the internet, if it was published before 1966, it's dicey whether it's going to be there or not. And some of the literature before 1966 is worthwhile, believe it or not. But for this experiment, my parents taught me, my mother said, okay, you got to kill some animals and find a rapidly growing tissue. Well, what tissue grows rapidly? So I go to the library and look it up. The testis is a rapidly growing tissue, and it's fairly easy to get free of the animal it's on. And then we decided to do some rats and some frogs in case there was a difference between cold-blooded and warm-blooded animals. And so my mother had this big scissors, and she used to just decapitate the animals with them. which was easy enough to do. So I learned to do that. And then I learned how to dissect out the testes and cut them up and fix them in Carnoy solution or Boone's solution. And so we fixed immediately, and then we fixed at 15 minutes, 30 minutes, an hour, 2 hours, and 4 hours. And then she taught me to run the samples through the alcohol and up to xylene and into paraffin and back into the alcohols, and then cut sections and then stain the sections with H&E, and then count metaphases. But this was like a PhD thesis, but I didn't know that. I discovered, so I went to college, and I said, you never learn to do any of this in college, even if you were taking biology. And then I went to medical school, and you never learn to do any of this stuff in medical school. And I discovered that some pathology residents learned how to do this. So I had acquired some skills which were unusual skills for anybody but somebody doing cytometry. And now, how many of you folks cut sections? Yeah, not a lot. Okay, so anyway, what we found out was that mitosis can continue after death, and we didn't try to publish this or anything, and I didn't get any national honors for my science fair project because it was rather sloppily. It was a pretty sloppy poster, but it was worth finding some. It was getting a project. If you do a PhD thesis, you have an advisor, and your advisor sort of suggests a project. Gets you thinking about a project, and then you go and do it relatively independently. But you've always got backup. Whereas if you're a postdoc, your advisor suggests a project, and you don't know anything about it, and he or she doesn't know anything about it, so you're really flopping around there. I did one of those, but that was when I was in college. Yeah. And it wasn't in cytometry. On the bookshelf, as I had mentioned in the first slide, was Casperson's book on cell growth and cell function, which described how he would do UV microspectrophotometry to measure total nucleic acid and protein, with 260 for the nucleic acid and 280 for the protein. We're using a spark gap for the light source and a galvanometer, basically watching a galvanometer wiggle around to get the intensity. So Casperson had a sort of a scanning microspectrophotometer, but it was kind of hard to do any, more than a few points per cell because it would take forever. And one of the people on my mother's thesis committee was a guy named Milan Kopach actually, and he built this video microscope. And I thought that was kind of neat because I used to lift tubes from my mother's electron microscope to build radio and audio gear with. And so this was really cool. And an electronic not an electron microscope, that was old hat, but an electronic light microscope, that looked like fun. And so here is a list of some flow cytometrists from the former Dutch colonies on the East Coast. And here we have the Herzenbergs in Brooklyn. This is Brooklyn College. It was a block away. This was my nursery school and my graduate school. And here are Len and Lee in the sometime around 1950. And so when Len got the Kyoto Prize, he said that the two professors who influenced him most were at Brooklyn College were Seymour Fogel, or Cy Fogel, who was a geneticist, and he ended up as head of genetics at Berkeley. And then Priscilla Polister, who was an invertebrate zoologist, and she used to get, she went with Steinbeck to get samples down on around Monterey, where this was where the whole Cannery Row thing was coming together. But Priscilla's husband was Arthur Polister, and he was at Columbia, and he was doing DNA spectrophotometry as Casperson was, and his student Leonard Ornstein, was also doing it. So both of these folks were involved in early image cytometry projects, including Kamensky's project. So there was all of this interaction here, and so Brooklyn had a lot more influence on the development of cytometry than I had thought. I never knew all the details of this until I was asked a couple of years ago to do a memorial talk for Len at the ESCA meeting, which was in Lisbon in 2014. And so I put all these things together. And even the other day, I was never. Well, Lee said she wasn't exactly clear how much Len knew about what Arthur Polister was doing, but I'm sure he knew quite a bit about it, and I'm sure that was one of the things that made him think about building a cell sorter instead of just buying 100 microscopes and 100 micromanipulators and finding 100 graduate students to pick the cells out. So the early motivation for cytometry was cervical cancer screening, because the pap smear, which was originally a way of studying fertility in monkeys, had been discovered to be related to the development of abnormality and cancer in the human cervix. And so the interpretation of that was pretty arbitrary. And so by the 1950s, we were beginning to have computers and some automated image analysis, very primitive level, and they thought that improving that could improve the accuracy of interpreting pap smears. And the spin-off from that is that, diagnosing cancer is kind of a heavy thing to do, and so reading white cell counts, differential white cell counts, that was a little easier. Everybody had those, and if you goofed on the diagnosis, it's not like a pap smear for leukemia, the average blood smear. So that was safer to work on and theoretically an easier program. So anyway, I got Ted Young, whom some of you may know, who was an ISAC icon, who ended up in the Netherlands, from the U.S. to the Netherlands. He was knighted in the Netherlands, in fact, and he was very influential in the development of image cytometry from the 60s on, and I ended up working with some people at the National Cancer Institute and the National Institute of Neurological Diseases, and roping in my very good friend Phil Stein, who is unfortunately no longer with us, because Phil Stein was working at the then Bureau of Standards, now called NIST, and NIST still does cytometry. They've been very influential in fluorescence standardization, but so what we were trying to do is build an automated microscope, and the people, Russ Kirsch, who was very good on image analysis, and Lou Lipkin, who was a very good pathologist, neither one of them knew anything about how to actually build equipment that could be made to move reproducibly under the control of a computer. And that was where Phil and his colleagues at the Bureau would shine. And so we went on with that, and so we built this thing which was called Spectre 2, from the James Bond, and so there's a microscope here, and we didn't have a mouse, but we had a joystick. So it took us 2 minutes to scan a 256 by 256 pixel scan of one cell, 2 minutes per wavelength. So 6 minutes per cell. So doing 10,000 cells for a pap smear, we figured the woman would need another pap smear by the time we got finished. And that was when I heard about this project that was going on at IBM to automate the pap smear not using a standard microscope. And so that was of interest to me. But what we had to do at NCI was to build a machine that could read autoradiographs, because we were trying to study the kinetics of DNA synthesis in leukemic kids. And the way we could do that was with tritiated thymidine. And I said, gee, within 10 years, there's going to be a way to do this in flow. And in fact, there was. It was Bob Leaf and Howard Gratzner came up with the bromodeoxyuridine labeling technique, and we now have click chemistry. We've got this, it's much easier to do. And so you don't need autoradiography to do it. When was the last time anybody saw anybody do an autoradiograph? In the past 10 years, anybody? Okay, yeah, but it's not common. Not as common as flow cytometry, obviously, and a little less radioactive. So we had Spectre 2, and my tradition of playing jokes here began even that early. So we had what we called a scanner head, and what was the cursor? Do I have a cursor here? Oh, I'm not on the pad. Yeah, so we had the scanner head. So this is a real scanner head. It even has a flush handle. And this is in science. And I don't think, no comment was ever made on this. We sent the paper in, we were invited to send the paper to Science. We said for their instrumentation issue, we sent the paper to Science, and we had comments here, questions here, questions there, but nobody ever picked up the flush handle and the toilet tank in the diagram. So that stuck with me. Well, after I'd been at NIH and decided, doing a few years more of clinical work, that I didn't want to be a surgeon like my dad, and I certainly didn't want to be a medical oncologist, not back in the early 70s. So I went to work. I figured that we, in order to build automated cytometry equipment, you needed big time grants. And somebody who was just a few years out of training was not likely to get big time grants. So I discovered that there was this company in Chicago called Searle, which was a drug company that was diversifying into medical instruments. And they were looking for people who knew biomedical instrumentation. There were really not too many formal biomedical engineering programs were just getting started back there in the 60s. But anyway, so they were paying good money, and I went to work for them. And one of the things I had to do is look at proposals that came from other smaller organizations to develop hardware. So after I'd been there for 4 or 5 months, these guys walked into my office and they said, we want to build a hospital hematology counter, which is going to have 5 beams, a flow cytometer with 5 beams that'll measure 8 parameters at 30,000 or 50,000 cells a second. 3 parameters of 50,000, 8 parameters of 12,000, and all computer controlled and blah, blah, blah. And I by this time I knew Lou Kamensky, and I said to Lou Kamensky, you gotta use a different wavelength. You gotta get more wavelengths. And so these guys, just walked in off. I'd never heard of them or seen. They turned out that this was a company that built the first Fourier transform IR spectrophotometer. So they were used to building machines that had mini computers in them. And my friend Phil was interested, and the Bureau of Standards people were doing that. And Kamensky was doing that because he worked for IBM, so he could stick a computer in his instrument. And nobody else did anything with computers. But in by around 1970, there was a small group of us that was doing this stuff. And so when we tried to get BD interested in making this machine the front end for a sorter, Bernie Schur and Mac Fulwiler told us nobody was ever going to need all those beams and all those parameters. And so now how many beams? They were up to 12 beams and 50 parameters or something like that. But that's because, so I always wondered about that, and that's because it wasn't until about 6 months after we had this conversation with Bernie and Mac that Lee and Len returned from Milstein's lab in Cambridge and had the blueprint for proceeding with monoclonal reagent development. The block engineering group was probably the biggest one in the world in flow. And we had a lot of extremely smart people. You might not understand this, but I used to call this the 1927 New York Yankees of optoelectronics. It was Myron Block just assembled a group of incredibly smart people, and so we were always. I learned optics from these guys, and that was very helpful. Thomas Hirschfeld was the chief scientist at Block. And he really was pushing single molecule detection back in the 70s. And so I was very pleased to see that the Nobel Committee's citation for the 2014 Chemistry Prize, which went to Eric Betzig and Stefan Hell and Merner, Merner's lecture and then the committee citation for the prize mentioned Thomas's work as sort of being pivotal in the genesis of single-cell measurement. Unfortunately, most of the people that I knew who would be interested in hearing about that are either not here or incapacitated, so it was a bittersweet recollection there. But here's detecting bacteriophage, and this is 79. It was presented at the ELMA meeting in 78. The second paper on detecting virions in flow cytometry appeared in 1999. And then that stuff, that instrumentation was picked up by Norm Dovicki, who was a postdoc out at Los Alamos with Dick Hiller. And so Norm eventually developed the capillary sequencer, which basically uses flow cytometer optics. So that had a big impact on genomics as well as on cytometry. Okay. So by 1980, I had been given a block prototype. We discovered, the outcome of the block project was that we discovered with an 8-parameter machine that once you threw up all the 2x2 displays, we could actually do the hematology with two scatter and 2 fluorescence and 1 laser. And we needed 2 dyes instead of 3. So that got around all the patents that Block had. And I said, well, this is wonderful. We can make a cheaper machine. And they said, no, it's not. We can't protect the cheaper machine. And that's the way the industry has been pretty much ever since. That you can have very fancy machines, even if you try to make a cheap CD4 counter. So if the box costs $5,000, then the consumable has to be more expensive so that there's something on which you can make money. And many of the companies that went into this were just adding unnecessary patented technology to what they were doing so that they had some way of making a profit. But they don't realize that if somebody else can do it without using you can get around your method, that doesn't work. So eventually you have to squeeze the nickels and dimes out. Okay, so 2015, so in 1980 I needed to start designing a flow cytometer and figuring out how to make the block instrument simpler, because I was in a relatively underfunded and understaffed academic lab and had been just bequeathed this thing that was too complicated for me to run. So we also had a cytofluorograph from Biophysics Systems / Ortho, and we basically, by creating a Frankenstein monster, that became the Cytomet. And so then I helped other people build them, and I needed to write a manual for them, which was called Building and Using Flow Cytometers, and we printed it on red paper so it would be hard to copy. And then I decided, well, maybe somebody else wants to buy this, so I sold a few dozen copies at $200 a copy, which was not a bad price. And then when in 1983 or thereabouts, Alan R. Liss was looking for a cytometry book, and I said, well, I've got one. And they said, okay, gussy it up and we'll print it. So that was Practical Flow Cytometry. And 2015 was the 30th anniversary of Practical Flow, and it was the 50th anniversary of the science publications by Kamensky on the flow cytometer and by Fulwiler on sorting. And it's also the 350th anniversary of the publication of Robert Hooke's Micrographia. How many of you have read Micrographia? A show of fingers? No. Gee, that's terrible. This is Robert Hooke we're talking about. We are here in Great Britain. Oh, Paul's looked at it. Yeah, okay, good. Yeah, Paul Robinson must not be in the audience. He's read Micrographia forwards and backwards. Yeah, this is a great book. It is written, despite the Latin title, it's written in English. And it has all kinds of stuff in it, among which speculation about, does the moon have gravity, universal gravity? This was a joint project between Hooke and Newton, at least until Newton got pissed off at Hooke. Now, the only known portrait of Hooke disappeared after Hooke had died when Newton became the head of the Royal Society. The Royal Society had a portrait, it disappeared. And, so Newton's comment about standing on the shoulders of giants was supposedly a subtle dig at Hooke, who was shorter than average. So, and I think, Isaac Newton must have been a nasty little prick. And then I realized the nasty prick is beyond dispute. But the little is an issue because statistics was not there. Nobody knew, there were no vital statistics in the 1600s. And of course, vital statistics developed here in the UK with Grant, and they started having listing causes of death and things like that. So this was a great advance in public health, but the statistics weren't there. So nobody knew what the average height was really, except it probably wasn't what it is today. Anyway, Samuel Pepys wrote this diary entry in 1665. This is the most ingenious book he ever read in his life. This is a very good piece of science writing, and you really should read it. And of course, Hooke never really saw cells. Well, here's something about, so Leeuwenhoek saw cells, and some other people might have seen cells. And here's a little verse without music, which I will let you read. And then you can read the right column with the comments. Now, the really interesting thing, so this was published in 1665, and Leeuwenhoek didn't start communicating with the Royal Society until 1673. And the story is that Leeuwenhoek, somebody had showed Leeuwenhoek, who couldn't read English anyway, the micrographia, and there were some pictures in micrographia of enlargements of about 30 times enlargements of fabric. So you could see the weave of the fabric. And the thought was that Leeuwenhoek, who was a draper and a tailor and a dealer in fabrics, was interested in using lenses, magnifying lenses, to assess the quality of his goods. And then he became a monomaniacal hobbyist and ran off and did all these things and eventually, discovered microorganisms. He saw moving sperm. Now, the thing is, if it moved, it had a soul. That's what animate means. So this was, if you read micrographia, there is no discussion of focus. I think the term is mentioned once, but you realize that focus in Latin means a hearth. And the cognate words of focus, feu in French, fuego in Spanish, fuoco in Italian, all mean fire. And so what is the focal point of a lens, which was, that's not mentioned in micrographia. It's not mentioned, I think it's mentioned in Newton's optics. The focal point of a lens is the lens where the convex lens starts the fire when you put it you put it its focal length away. And focus as a verb was not used as a verb until the 18th century, the early 18th century. So we have coined words to describe things that have never been seen before. And so if you look in micrographia for cells, if you look on the internet, it says Hooke analogized cells to the cells in a jail or cells in a monastery. Well, no, he didn't. He made an analogy to the cells in a honeycomb, which were more regular, but he realized that what he had in cork, what he saw in cork, looked the same in a longitudinal or transverse section. So they couldn't have been tubes. They had to be small compartments. And he said, well, they're like the cells in a honeycomb. And cyto, CY, the prefix for cell, is in fact Greek, and it would be pronounced kudo because it's kappa, upsilon, tau, omicron, but kudo was already borrowed from the Latin to mean skin. So they shortened the K to a C, and that's why we call it cyto. So that was meant, and if you go look up the concordance to classic Greek, you find that prefix from Aristophanes, the wasps, as describing the shape of the chambers in a wasp's nest, which is, that's really kind of neat. But so Hooke probably never saw cells, and not before he wrote micrographia. After he was assessing Leeuwenhoek's work, he duplicated Leeuwenhoek's experiments, and they both used microfluidics, as I have written down there. And they have attempted to be cytometers to measure cells. And interestingly enough, Spinoza played a role in this. There's an interchange. Everybody was, the Royal Society is a fascinating organization, but it probably took a couple of weeks to get communication from here to the continent, even to the nearby continent. But there was all this interchange of letters and the Royal Society publications themselves. So Henry Oldenburg, who was at one point the president of the Royal Society, would correspond with people on a wide variety of subjects. And there's some correspondence in November 1665 between Oldenburg and Baruch or Benedict Spinoza. And Spinoza wrote about, envision a worm in the blood looking at the cells of the blood and the lymph and looking at the particles, not cells, because nobody used the term cells. Envision looking at the particles of the blood and the lymph and the chyle. Well, you read that today, particles, yeah, sure, blood cells. He's talking about blood cells. But that was one of the first possible descriptions of blood cells. We know that Malpighi had described red cell rouleau by 1665, but Spinoza, okay, so Spinoza was known for his philosophy, but his day job was making microscopes, and we know from correspondence between Spinoza and Huygens that he made high-powered microscopes which had small depth of focus but high magnification. So it's very likely that and you see what happened. Spinoza, if he's looking at through the microscope, nobody's bothering him. If he's talking about the universe, he gets excommunicated. Same deal with Galileo. Galileo looked through microscopes in the early 1600s. You look through microscopes, he never got into trouble doing that. You look through telescopes, he got house arrest. So stick to cytometry. Yeah. Okay, now the birth of the cell, I actually had an email exchange with the late Sir Henry Harris, who wrote a wonderful book called The Birth of the Cell, and that's a must read. You can put micrographia off for a while, although you'll like micrographia, but The Birth of the Cell is really a marvelous book because it talks about all of the politics that went behind cell biology. As you know, there are scientific controversies and there are scientific fights and there are rivalries and there are just misinterpretations and all of the above. Everybody made mistakes. Virchow made mistakes. So it's really interesting to read that, because if you go through school, even if you learn a little bit about Schleiden and Schwann and the cell theory, it's like it all came into being and everybody bought it right away. But the cell theory as it came out did not rule out spontaneous generation in certain cases, and there was no knowledge of how cells divided. There was no knowledge of mitosis. I mean, basically, Virchow had said that cells, nuclei divide by binary fission, which they demonstrably, after we had, there's another word, chromosomes, right? See, we didn't have chromosomes until we had dyes. And the dyes get me more to a topic I hope I'm not running too terribly late, okay. So the dyes get me to a topic like Virchow was he decided that pathology should be on a cellular basis. And so it was fairly easy to tell red cells from white cells, but it was not easy to tell the white cells apart because most of them didn't have any coloration, whereas the red cells were full of hemoglobin. So if you looked dark field, and basically, most old microscopy was dark field. We didn't have substage condensers. So if you obliquely illuminated something, you basically got something that combined a light, bright field and dark field image. You can go all the way to dark field. Well, if you look over here, you have, there's some granulocytes, neutrophils, and a lymphocyte, and an eosinophil. And the eosinophil, my finger is not showing up. So there's an eosinophil, and you can see there's a little more scatter signal, side scatter signal from the eosinophil than there is from the neutrophils, and there's very low side scatter from the lymphocyte. So, but that wasn't too wonderful, and so Paul Ehrlich in the 1870s, as a medical student, decided that the affinities of different cells. The chemistry of cells could be deduced from their ability to bind different colored dyes with different chemical properties. And he had access to synthetic dyes because over here in England, an institute of chemistry had been set up in London in the the early 1800s. Now, the Industrial Revolution started here, and the Industrial Revolution ran on coke. And it ran on coke, and it ran on coal gas, because the gas light started in the early 1800s. So the coal was being, what they say, destructively distilled to make coke and to make coal gas, and what you would end up with was a byproduct of coal tar, for which there were no uses. But coal tar could readily be treated to form nitrogenous organic compounds, one of which was aniline. Now, why this was interesting to the organic chemist August von Hofmann, who had been imported from Germany to teach organic chemistry in London, this was of interest because it was known that quinine, which was just isolated in 1821 in France, was an organic nitrogenous compound. And von Hofmann figured that if you took aniline and you did A, B, and C to it, you would get quinine. And quinine could be used to treat malaria. Now, malaria, there's an interesting story. Malaria has been with us for thousands of years. But we have, so in the 1500s, we had a situation much like the situation we have with ISIS now. There was an organization, there was a state, a failing state, which was taken over by a bunch of religious fanatics who raped the women and killed the men. And these guys were Pizarro's troops from Spain. And accompanying them were Jesuits. And among the Jesuits were people who were studying all the plants and animals of the New World. And at some point, it was discovered that the Indians were using this tree bark to, when they got chills from being in the cold at high altitude. And so the Jesuits made a leap of reasoning that didn't, in retrospect, make any sense, but was very lucky. They said, well, shaking chills are accompanying malaria. And malaria is killing, like about every third pope was dying of malaria, because Rome was a malarial swamp until it got cleaned up by Mussolini, of all people. So the Jesuits brought the tree bark back to, and so a trade in the tree bark was established. And once it was, so you'd buy the tree bark, and there's no quality control on that, and it was expensive. So they figured out, hey, if we can synthesize quinine from coal tar, we got it made, and so Perkin went into the lab. He was an 18-year-old student, and he went into the lab and he did what Huffman told him, and he got this purple stuff, or mauve. And this was, von Hofmann said, well, quinine is colorless, so why don't you go back to the drawing board? You're fucked up. And von Hofmann said, Perkin recognized that by 1850, England, which had been importing woven fabric from India, was exporting woven fabric to India because they had power weaving. But dyes were expensive because and the natural dyes were not very good. And so Perkin said, this stuff is, a drop of this will stain, 20 yards of material. And so he found people in the textile industry, and they bought this stuff. And it was a favorite color of Queen Empress Victoria. It was a favorite color of the Empress Eugénie, who was the consort of Louis Napoleon of France. So this was high fashion, and dye industries emerged from that. And the dye industry was turned by Ehrlich into the drug industry. Not everybody knows about Ehrlich treating syphilis, but the first successful chemotherapy by Ehrlich was that he used methylene blue in 1891 to treat a couple of cases of malaria, and it worked as well as quinine. Not any better than quinine, but it worked as well as quinine. And the company he bought his methylene blue from was in Hearst, and changed its name to Hearst sometime later. So this is the IG Farben conglomerate. They started as dye companies, and they became general chemical companies, and then they became drug companies. And high throughput screening originated with Ehrlich. And so Ehrlich was staining blood cells, and Romanovsky and Giemsa and other people were adding futzing around with stains to identify malaria. Well, why malaria? Malaria was the only curable disease. You know, if you found somebody had malaria, if you could diagnose malaria, you could treat malaria with quinine, because there wasn't any drug resistance to malaria at the time. And so, so now, you know, gin and tonic originated because the empire had to be maintained by British people, and they were dying of malaria. So if they took quinine, they wouldn't get malaria, and quinine tasted awful. But if you added gin to it, it became palatable, or at least you forgot that it tasted bad. And so now we should drink gin and Giemsa. So going back to the Bible of flow cytometry, why is practical flow cytometry like the Bible? A lot of people swear by it, many fewer people do what it says. But we are enjoined to keep the corners of our field, you know, let the stuff that accumulates in the corners of our fields be fair for the poor and the stranger. And yeah, anyway, so we have some very fancy stuff, and some of our very fancy stuff, I mean, you can't take a 10-beam, 30-color flow cytometer to sub-Saharan Africa and use it to diagnose malaria, and you don't need it. And we got to figure out how we can teach people there to build something they can use. Now, simple cytometry sort of got going about 1999. And so about 1999, we were also considering the problem of AIDS in Africa. And so somebody asked me to make some cheap red laser flow cytometers to do vaccine trials. And I said, you know, the flow cytometer, if it cost a nickel, would be a little too complicated to use where there's no water and there's no power. And so you could do this with an imaging system. So a lot of people got to work on that. And so by 2011, Alaire came out with this box called the Pima, and by last year, BD came out with the Fax Presto, and both of these things are imaging cytometers that'll do a CD4 count by looking at CD3 and CD4. So in 2000, I exhorted the cytometry community to work on simpler machines for not only for HIV/AIDS, but for malaria and TB and other infections. And I am sorry to say that CD4 was the only thing that anybody did any serious work on. And wouldn't you know, ironically enough, in September 2030, the World Health Organization decided that anybody diagnosed as having an infection with HIV should be put on antiretroviral therapy regardless of CD4 count, so there was no need to do a CD4 count. And that will, of course, drastically reduce contagion, because once you're on antiretroviral therapy, your viral load drops. So if you just use viral load for monitoring, you don't have to bother with CD4 at all, unless you have some immune system problem. Well, we are dealing with antiretroviral therapy. We're dealing with drug resistance. Not so urgent right now with the antiretrovirals, more urgent with TB and even with malaria. A portion of the 2015 Nobel went to Tu Yu from China, who had isolated artemisinin, and now there are people taking small flow cytometers, people taking Accuries into Africa and Southeast Asia to look at drug resistance. And the point is, well, my point is, they don't need Accuries. They could do this with imaging machines, with simple imaging machines. And here's a paper from Cytometry, which came from Harvard. This uses imaging flow, but very simple, relatively inexpensive imaging flow, and it can basically do a complete blood count. And it could be built with a Raspberry Pi, as I have shown in the side panel there. Another British product, another Cambridge product, as a matter of fact. Really useful gadget. Now, in malaria is a disaster, because with HIV/AIDS, it was pretty clear that you had to use monoclonal antibodies and cytometry, or you at least had to use monoclonals to do diagnosis. And with malaria, everybody assumes cytometry equals expensive and cytometry equals complicated. And so here, if this is a fantasy here, this is a scanning EM of red cells onto which is superimposed a two-dimensional image from a Giemsa stain smear, whereas it happens the nuclei of the parasites, ring forms, are colorized blue. But if you use Wolfgang Goethe's little microscope, you get blue nuclei on a black background where you stain the cells with DAPI. You could stain, and so basically you can do this stuff with a very simple imaging, and you get much better specificity than you get with Giemsa. I mean, Giemsa, people are trying to automate Giemsa. It's ridiculous. And, so malaria goes way back. And now back to decades of logs. Now we have the log of decades. If you have a six decades of decades, you get up to 1 million years. Well, malaria probably has been around for 1 million years. We know that at least 3,000 years ago, King Tut had falciparum malaria. And when Laveran discovered the parasite, he discovered it based on the fact that the parasite was motile, which is the criterion for Leeuwenhoek to identify things as alive. And they contained hemozoin, which is this pigment that they make by digesting hemoglobin. And Romanovsky, whoops, wrong typo. Romanovsky was mixing eosin and methylene blue and azure dyes, and he found that this improved visualizing parasites. In Giemsa in Germany refined that in 1904, and I don't think, until that point, I don't think anybody had ever looked at a malaria slide under an electric light. But the Giemsa is still the standard, and there are much better dyes now. And so, but the reason that malaria was important in hematology, why did Giemsa become the standard stain for all blood analysis? Because when people started analyzing blood with microscopes, they were more often than not looking for malaria. Because while they knew leukemia existed and they knew anemia existed, they didn't know how to treat leukemia or anemia. And they knew that if they found malaria, they could just treat the patients with quinine. So there are all these pictures of, how do you tell these different strains of malaria apart? Not by eye. And one of the best ways of doing it is with DNA-based composition. So Giemsa, we got to get rid of Giemsa. And here's my take on that is that Giemsa, down through the years, it's the stain we use on all malaria smears. New solutions should now be tried. We've gone far too long with Giemsa on the slide. Other dyes we have today quantify cells' DNA, base by base, and RNA stains added to the brew. Get all stages identified with much better counts than Giemsa on the slide. Hemozoin we visualize, needing neither dyes nor eyes. Long wave red light one applies won't easily go through. Trained observers can step aside once we've gotten rid of Giemsa on the slide. Now, talking about better counts, student at the Guinness Brewery discovered that counting blood cells and counting a lot of other things obeyed what we now realize were statistics first described by Poisson in the 1830s, but the student was kind of new with them. Anyway, so this was published in Biometrica in 1907. By 1910, Ronald Ross, who discovered that malaria was spread by mosquitoes, this was a rare event analysis, so he wanted to know how much blood do you have to look at to diagnose low parasitemia, and he used the Poisson calculus, student type calculation. So that, this anticipates any other rare event analysis that I know of in cytometry. And it happened here. And it turned out that methyl green and pyranine Y, which Ehrlich used as stains, are much better blood stains for malaria and for diffs. And pyranine Y is a good RNA stain, and Darzenkiewicz, I used it with Herxt for DNA, pyranine for RNA. Well, Herxt is only fluorescent when it's bound to AT, and methyl green binds to AT. So basically, there is now, methyl green is now an AT sensitive. You can use it in fluorescence. That was just demonstrated in Uruguay a couple of years ago. So you could actually make a fluorescent methyl green pyridine stain, but it's easier to use Herx than Herx pyridine thiazole orange, or if you want to do base composition, Herx and pico green. And it was shown back in the mid 80s that if you measured the DNA and the RNA in malaria parasites, you could tell all the stages of development. And it was shown back in the 1980s also that the Herx dye signals from Plasmodium falciparum and Plasmodium vivax were different because falciparum is 80% AT in the DNA and vivax is only about 57%. So even though the vivax genome is bigger, the falciparum genome is brighter with Herx stain. And you can do that with a very simple machine. So anyway, this got lost in the literature because that was published in the Journal of Histochemistry and Cytochemistry. The malaria people didn't read it. In 2008, Brian Grimberg in Cleveland, doing his cytometry with Jake Jacoberger, who did his PhD thesis on malaria in 1981, they showed that you could do this DNA and RNA staining and you could find all the developmental stages. So you can discriminate species doing that. And if you look at the malaria pigment, one of the ways of doing that is with depolarized scatter. Well, depolarized scatter used to be the subject of a patent held by Abbott, and they used it to pick up eosinophils, which don't happen to have hemozoin, but they do have birefringent granules. So people with malaria were kind of stuck. Partech would put a polarized scatter measurement on your machine if you asked them to, because they weren't afraid of Abbott, but BD and Beckman Coulter wouldn't. Cytomation wouldn't probably. And so I put one on the Cytomut. We played with this, and it turns out that hemozoin is basically malaria parasites eat hemoglobin, they shed hemozoin, and so as they develop and multiply within a red cell, you get more and more hemozoin. Then in the asexual stages, the red cell eventually pops, releases merozoites, and they free hemozoin. But the gametocytes contain a lot of hemozoin, and you can spot them, and they're usually fairly scarce. So it's very interesting to look at species. It's helpful to have a hemozoin measurement. Now, you can do that, as I said in the song, with a fairly simple gadget. And so here is one of these things from a group that's going into the Cambodian-Myanmar border, which is a hotspot of artemisinin resistance, and they're demonstrating resistance. They're demonstrating chloroquine resistance here in P. vivax, and that methylene blue can be used to treat this. As I said, Jin and Gimza. But the question is, do you need to take an Accuray, which would probably, a standard Accuray would be about 50,000 American dollars if you're taking it into, and then if you want to do Herx, then you want a UV diode laser on it, it'll be about $70,000. And you don't need that because I've been trying to do these low magnification imaging systems, which were sort of inspiration for the Pima and the Fax Presto, but nobody tried to look at TB and malaria with them. And TB and malaria, it turns out it's hard to get malaria samples in the US, or probably it's hard to get them in the UK, especially for multiple species. So unless you get them from travelers, there's nothing there. You got to go to Africa, you got to go to Asia. And it's very helpful if you can look at a slide. The same thing is true of TB. Now, if you have a blood slide, you treat it with methanol for 30 minutes, you can kill Ebola on it. If you have wet blood, and where there's an Ebola epidemic, you don't want to deal with that. You don't want to have to keep that around. So you can make a very simple machine that'll do this, and you could use it. Doctors with Borders could use you do blood counts. You can do a whole bunch of microbiological and immunological analysis, and nobody has built this because nobody can figure out how to make money on it. And I claim that people where the malaria is and where the TB is, they are less concerned about margins and more concerned about keeping people alive, and they would could make a business out of making this stuff, and what you have to do is get together with them and teach them how to do it. So that's my aim. And I was saying it would be very nice if each of the flow companies would donate what they pay for one ISAC party to the fund here. But I don't know if that's going to happen or not. Anyway, so Georgia on My Mind was the song about Giemsa, and I sent that down to CDC, and that went over well because they're in Georgia. But then I had to give a talk in North Carolina, so I can't sing Georgia in North Carolina, so I had to do another malaria song. Now these pictures were drawn by Dr. Seuss when he was working in the army. He was in the army in World War II, and he was helping put out pamphlets, and one of the pamphlets that he put out were how to avoid malaria. So he's got Anne Nopheles, who drinks blood and is dying to meet you. So we have now, since the Ebola, it's been argued that Ebola and Zika might be scarier than malaria in the area. I mean, sexually transmitted Zika, who knew? It gives a whole new meaning to getting a little head. Nothing could be scarier than malaria in the area in the morning. Vectors that have flown up give you pathogens they've grown up without warning. When you get plasmodia from mosquito bites, once they've said hello to you, they might punch out your lights. Hope that some MDs are in and give you artemisinin in that morning. And that drug resistance doesn't make the doc's assistance all in vain. Even if the parasites don't go to your head, they're apt to make you wish you were dead. Nothing could be scarier than malaria in the area in the morning. Thank you very much. It's been fun. Any questions?
Any requests for songs? Can you do There's No Business Like Flow Business for us?
Yes. There's no business like flow business when show business is slow. Where else can you play around with high-tech lasers and computers and sell clones? I go in the lab each day and try techniques out with my tech. It's in my bones. There's no people like flow people. They smile where lights are low. Even when there's mycoplasma in your cells, your laser smokes and emits bad smells. Still you wouldn't trade it for a stack of gels. Well, I wouldn't, I know. Let's go on with the flow. Yeah, but of course there is a business like flow business. So I won't sing that song.
Thank you very much. Thank you very much to everybody who's attended the meeting. Thank you to all of our keynotes. Thank you to all of our speakers, and also a big thank you to all of the vendors who have helped to support this meeting. There is some lunch available. I wish you all a safe trip home, and we look forward to seeing you at one of the future FlowcytometryUK meetings. So, thank you.